the last day, the afternoon session. The first is, of course, tutorial talk by Professor Subhro Bhattacharjee from ICTS Bengaluru. So Subhro continues with his near field description for quantum spin liquids, I guess. Yeah.
Okay, so welcome back. So I'll continue with whatever I started out with, but Arnav already gave an alternate version of the same thing. Basically the construction that I'm trying to present is a mathematically simpler version of what Arnav was pointing out, which is more experimentally relevant. Sure, that there is this funny thing that the simplest thing may not be immediately experimentally relevant, and vice versa. So it's basically the same ideas which I'll summarize and then move on to approximate things. But the idea is the superposition of loops, etc. Here, the calculations are slightly simpler in the sense that you're always dealing with 2x2 matrices, whereas there were rotors, but essentially it's the same ideas, and we will land up with lattice gauge theories, which I'll argue is the natural mean field theory for spin liquids. Okay, so let's remind ourselves this was the system that we were trying to study. And then we explained the structures of these operators and constructed the ground state, okay, which was this superposition of loops. Let me try to reiterate this point that the quantum ground state is not degenerate macroscopy. Okay, so there were some questions, I think, after my talk and also during Arnav's talk or after it. The quantum ground state is not degenerate. Okay, so it is in accordance with the third law of thermodynamics that individually all these are classical ground states. So once you switch off the quantum terms in Arnav's case, the ring exchange term, the 6-bit term, each of these were individually classical ground states. That's where one had the degeneracy. But once the quantum term is switched on, the degeneracy is completely lifted. So the thermal entropy is completely gone, and we have a state which is in accordance with third law of thermodynamics. Okay. Here also, basically, one can think about the B term, which is like the sigma z term, okay, as a classical term. Okay, and if you think about only B term, put J of S to be 0, so that there is no A term, then all these states are individually ground states, okay, of only the B operator. Okay, but once the A term is switched on, so there the only B model has a lot of degeneracies of ground states. But once the A term is switched on, or you make J's to be non-zero, only one particular superposition is chosen. All other superpositions have higher energies. So the ground state does not have macroscopic degeneracy. Okay, so this is very important that the thermal entropy is gone. Okay, but we don't have symmetric breaking. Okay, instead we have lots of superposition, and we will need to characterize this superposition more clearly. Okay. So I wanted to clarify that point. Questions? Okay, then. So let's move on to excitation. So that was the ground state, and it does not have symmetric breaking because all these contributions, if I think about one particular spin, it might fall on the loop or it might not fall on the loop. Let's go back to this. So since I have lots of loops, if I think about a particular spin, it may fall on the loop or it may not fall on the loop with equal probability. So if I sum over the average contribution, it's 0. Okay, and all correlation functions are exponentially decaying, so there is no symmetry. Okay, if you start with these kind of states. Okay, so let's So that was the ground state. Let's think about the, so that's the analog of that is the all up or the all down state in the ferromagnet if I was thinking about symmetry breaking. So that's the ground state. But here, there is no symmetry breaking. Okay. Good. So now let's think about the excitation. Now I need to contrast this with the analogs of spin waves. Okay. And I've already pointed out an example where there was a gapless excitation, but there was no broken symmetry. Okay, and the gapless excitation was not a Goldstone boson, but a gauge boson or an emergent photon case. Okay, so we need to study the excitations in this case too. Okay, good. So what are the excitations? The excitation is basically at the ground state, all the AS and the BP were +1. You just flip them. Okay, so you flip them, you create an excitation. Okay, so remember the AS operator was product of sigma x, and the BP operators were product of sigma z. Okay, so let's go back and try to see how can I create excitation. Okay, suppose I take the ground state. Okay, I take the ground state and act it with a sigma x operator on this side. Okay, so the sigma x operator commutes with the AS operator, which is itself a product of sigma x. Okay, but it anti-commutes with the BP operator because on this placket and this placket, because the BP operator on this placket and this placket contains a sigma z term. Okay, so then it basically flips the sign of BP on the two plackets. Okay. So it flips it from +1 to -1 on both these plackets. Okay, so I have a excitation on this placket and an excitation on that placket. Okay, immediately you can see that this is different from spin waves because I flip one spin, instead of creating one excitation, I create two excitations. Okay, now this again, I keep on reiterating that this is very similar to what Tom was pointing out. Now, suppose I flip, so I flip this SN, I act with a sigma z here, okay, sigma x here. So then this spin gets flipped, okay, but then the product of these becomes +1. So this excitation is not there, but the excitation moves here. Okay. So this is again analogous to the construction of monopoles that Tom was pointing. Okay. So and this second step does not require any more energy. Okay, because the two excitations moves to two excitations. Okay. So in a way, a single spin flip not only creates two excitations, but then after that I can move them away without any further change of energy. Okay, and this is in 2 dimension. Okay, so this fact that you can create a single spin flip creates two excitations which then can move away from each other is summarized in the statement, and this can be made more mathematical as I do, is that the single spin flip fractionalizes into two excitations. This is very different from the spin wave where you think about the single spin flip and then you basically take that single spin flip and sort of delocalize it using this superposition. Okay, so whatever the structure of the low energy theory might be, it must take into account this fractionalization that microscopic spin operators leads to more than one excitation. Okay, so this is a characteristic feature of the kind of ground state that we have been superposition. Questions? Okay, so that was about the BP operator. Instead of operating with sigma x, we could operate it with sigma z. Okay, now the BP operators don't flip because they're made out of sigma z themselves. But now the AS operators flip because they are made out of sigma x. And that creates two AS. Now they live on the sides of the square lattice. It's the same story. but instead of living on the brackets, they live on the sides. Okay. And now I use a series of sigma z operators to move them away. Okay. So I have these two weird set of excitations where every spin flip creates a pair of such excitation. Okay. And the point is that since sigma x squares to 1 or sigma z squares to 1, I cannot operate them twice. If I try to operate them twice, suppose I flip the spin once and try to operate it again, it flips the spin back, and so these are gone. Okay. So the number of excitation, unlike the spin wave, where the number of flip spin was 1 and it was conserved, okay, the number of excitation is not conserved. Okay, it's conserved up to a number 2. Either you can have an excitation or you cannot have an excitation. Suppose, say that if I don't have an excitation, the number of excitation is of course 0, and if you have one excitation, it's 1. Okay, but you cannot have 2 excitations. 2 is equivalent to 0. Okay, so this is what we know Ising spins are capable of. Okay, so these are in a way Ising excitations. Okay, so they are not excitations which conserves number. Okay, like bosons or fermions of the usual kind. They are the number of such excitations, the parity of the number of such excitations is conserved. Okay, in other words, whether I have 0 excitation or 1 excitation. Okay, for both A and B. Okay. Okay, I'll come to the word electric and magnetic in a moment. But these are the 2 classes of excitations. Okay. Questions. So then let's try to create these charges and move them around. Okay, and again you can do that very easily. In fact, sure, all of you can do this. Just writing these things down because all one needs to remember are the anti-commutation properties of Pauling matrices. Okay, is that suppose I created these 2 defects, these two charges or these 2 excitations of the BP type by creating a sigma x by acting with a sigma x here. So the original things, the original excitations were here and here. Okay, by creating. Subsequently, if I act with sigma x here and then here, this excitation remains here, but this moves to this. This is the same, and similarly for sigma z without any costing again. So if I think about operators, string operators like sigma x, sigma x, sigma x on this dotted line, okay, that's this operator, or that's this operator actually, it's a sigma z, okay. So this basically moves the AS excitations, okay. I'll soon start calling AS excitations as electric charge, and that's why they subscript electric, okay. So they have a starting point at S1 and an end point at S2, and you take a string of sigma z operators from S1 to S2. The actual path does not matter; the endpoints matter. Similarly, you can think about the sigma x operators. Okay. The whole point is that if I take this operator and I think about the AS operator, okay. It's a severe, yeah. So they act. Okay. So the point is that if I think about 2 electron, two AS type of excitations, okay, and this operator basically acts on these 2 AS excitations. So it anti-commutes at this point and this point. So it gives rise to 2 AS excitations at the 2 endpoints S1 and S2. So these are these AS or electric charge creation operators. Okay. But now, if I take this electric charge here. By electric charge, I mean the AS excitations, and we'll soon see why I call them electric charge. Okay, so if I take this electric charge here and I take this electric charge here, I can use another string operator like this to change the position of these two electric charges, interchange the position of these two electric charges. Move this charge from here to here and move this charge from here to here. Okay. It's again this sigma string of sigma z operators. If I do that, then because all I'm using are sigma z operators and all of it commute with each other, we will see that the two charges at S1 and S2 and the opposite thing, the two charges interchanged, the wave functions are basically the same. Okay? And this means that the exchange statistics between these two excitations are bosonic. Okay? So these charges, which are conserved modulo 2 Ising charges, also have a bosonic statistics, because if you interchange them, you basically get back the same two particle wave function. Okay, so this is for the AS excitation, the excitations that live at the sides of the square lattice. Questions? It's a exactly similar story for the magnetic, the other kind of excitations which live on the placket, which I'll call magnetic charges. Okay, instead of sigma z, you now use sigma x. Okay, and you perform the same kind of things, but now instead of the strings of operators living on this square lattice, you think about strings of operators living on this dual square lattice obtained by joining the midpoints like this. So this other kind of excitation which lives on the plaquettes, which I'll call magnetic charges, are also bosons. They will exchange and get the same, get back the same wave function. Okay. But if I think about, okay, so this we have already discussed. But if I think about the following thing, that I have an electric charge, okay, here, okay, I have an electric charge. I want to take a magnetic charge, grounded electric charge, okay, and this is what the electric and magnetic names becomes very useful. Okay, so suppose I have a type of excitation or electric charge sitting here, and a magnetic excitation or this plaquette excitation sitting here. Okay, I know how to move these things. If I want to move these things, I use a string of sigma z. If I want to move this thing, I use a string of sigma x. Okay, so I try to I know how to individually move this. What I want to do is that I want to move this charge, the plaquette excitation or the magnetic charge, in presence of the electric charge, actually around it. Okay, so what will I do? I'll take the sigma x, sigma x, sigma x. I'll take all the sigma x, and basically once I apply it here, the charge moves here and here, 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 and it just goes around. Okay, so essentially I have a string of sigma x operators. Okay, it's clear how I move the this yellow excitation or the magnetic excitation around the blue excitation or the electric excitation. But now I have all these string operators. Okay, all these sigma x operators. But I can just add the square, since square of sigma x operators is identity, I can just add, multiply them by 1 and resolve them as sigma x square. So for these two operators, these two operators were already there, but I have if I have these two operators and these operators, so this loop operator, which are products of sigma x on this loop, is equivalent to product of AS within this loop. Okay, so I just resolve once as sigma x square, and I create and I complete the AS operator for this side, AS operator for this side, and this side. Okay. Just resolve the 4 ones into sigma x squares. Okay. But now you see that AS on this is 1, 1, 1, minus 1. So the product of AS is minus 1. So if I have this excitation and I move it around this other excitation, this operator is nothing but product of the AS operators enclosed by the loop. And since there is one electric charge, the product of the AS operators is minus 1. Okay? So that means that if I move this yellow excitation around this blue excitation, okay, or this magnetic charge around this electric charge, the wave function is a minus sign because the product of AS is minus 1. Okay? Here, why this minus sign is coming from? So if I move this, in short, if I move this excitation around the other, I gain a minus sign, but minus 1 is e to the power I pi. So in other words, I gain a pi phase once I move the one excitation around the other. As if, and this loop can be arbitrarily large. Okay, so I can take this here, but this loop I can just extend. I can take this along the perimeter of this institute. Okay, and still, if there is one charge, it would detect that charge, this minus sign, just cares about the number of charges present. And as it is, the number of charges can only distinguish between odd and even. So if there is an odd charge, it just can detect it at arbitrarily long distance. Okay? So this is nothing but the Aharonov-Bohm field. Okay? And this is the reason why one calls this as electric and magnetic charges. So this blue thing sees the yellow thing, the yellow excitation as a source of pi flux, or the other way around. Okay, and then you can name one electric and one magnetic. The name doesn't matter. I just choose to name this as electric and this as magnetic, but you could do the others. Okay. So this basically means that the kind of excitations that I get in this very cartoon version of what Gordon was talking about already smells out of something like electromagnetism. Okay. Okay. So that's about electric and magnetic charges. Okay. Now one can think about taking an electric charge and a magnetic charge and bounding them together, like putting them next to each other in some way, this or that way. And there are many ways to do it, but putting them next to each other. Okay, so let's call that bound state an epsilon. Okay, we call this electric and magnetic. Let's call this bound state. So is it here what? So I put this electric charge here and take the magnetic charge and put it here. Okay, and that thing I called an epsilon. Okay, so now I take one epsilon here and another epsilon here and try to exchange two states. Okay, the combination of the arguments that I gave here, okay, to move the electric charges and magnetic charges, you would see that if I want to exchange two epsilon particles which are bound states of E and M, there would be at least one point where the where this Z string and the X string would need to cross. I will try to do this. You find that you cannot avoid one crossing of the X string and the Z string. But since X and Z, okay, that would give a minus sign. So that basically means that if I take two epsilon particles and try to exchange them, I get a minus sign. But that's what we know fermions are. If I take two fermions and exchange them, I get a minus sign. So what I have created is basically a low energy set of excitations. Two of them behaves like bosonic electric and magnetic charges, and their bound state behaves like a fermion. Okay, and this all involves only Pauli matrices. Okay, so this is doable.
Sir,
Yeah.
so when we make,
Just wait for this.
so when we create we create double excitations all the time, right?
Yeah.
So you have a placket and a side excitation here.
Hmm.
So you are just choosing one of these, is it? No. Or
So
you can
if you look carefully, I have these things. Okay, this and this. So it means that I have taken the other yellow thing, maybe in the next floor, and this somewhere. Okay. So I haven't violated that condition. Yeah. Just that I have not drawn them. Okay. More questions? Okay, so this is the analog of the Clevish-Gordon algebra for this system. Okay, just like you do Clevish-Gordon algebra for angular momentum addition. Okay, these are the Clevish-Gordon algebra, and basically generalization of that. That if I take an electric charge, so what I have explained, I mean, one can try to connect it up with various things, but this is what I have explained. You take an electric and magnetic charge together, okay, and it behaves like a epsilon particle, which is a fermion. If I take two electric charges, it's equivalent to having no electric charge. That's sigma z square is equal to 1. If there is two magnetic charges, it's equivalent to having no magnetic charges. That sigma x square is equal to 1. Okay, and then similarly sigma x square into sigma z square equal to 1. But now, if I have if I have a magnetic charge and an epsilon, it's like having two magnetic charges and an electric charge, which is what this is saying. This is a lot simpler than the Clevish-Gordon algebra that we are used to from quantum mechanics 101, but this has a lot of extremely important formulas. Okay, so it's basically saying that what are the low energy properties of these excitations. Okay, this, and how they transform, their statistics, etc. Okay. So I've now said you everything about the ground state and the low energy excitation, and I hope you're convinced that nothing looks like Fourier-Wise-Newton theory of the kind that we are used to. Okay, so I think I'll leave this out for interest of time, but one can try to understand the topological degeneracy of the system. Let me just quickly go through it. So instead of thinking about an open system, you now think about the same system on a torus. Okay, this is the picture that is the reason why I wanted to present this on the slides. Don't go on this. Okay, so you take this on the torus, okay, and you now think about operators. We are familiar with the string operators of X and string operators of Z, but now the thinking on the torus allows us to think about new variants of those operators, okay, which I'll call this ZX, ZXX, ZX, ZY, and XX and XY operators as follows. Okay, so this ZX is a product of the sigma Z operator running around this blue direction, which I call the X direction. So I take all the Z operators running along this LX line, which is this blue line. Okay, this blue line. And similarly, I can take Y operator, the Y direction. So sorry, for the change of colors. This is green, it's equivalent to this red here, it's a dark red, okay, solid red line, okay. So I can take the product of the sigma z operators running along this solid red line along these poles. So this would be like closed loop operators because of the rulers. Okay. Similarly, I can take the product of the x operators, but now along the dotted lines in the x direction, and similarly in the y direction, the product of x operators. Okay, these are 4 operators, extra operators that I have on a torus. Okay, and they are also Hermitian operators with squares to +1, so their eigenvalues are +1 and -1. So 4 extra operators on a torus. Okay, and if I try to find out how many of these operators commute, this is their algebra. So the x operators, of course, commute because they're all made out of sigma x, and similarly for the z operators. Okay, the x operator running in the x direction and the z operator running in the y direction do not commute because I have so this is the x operator running in the x direction, and this is the z operator running in this direction. This dotted blue line versus this solid red line, and they intersect here. So there is one sigma x into sigma z, which anti-commutes, and that's this anti-commutation. Okay, again, it's all anti-commutation. So basically, this says that I cannot simultaneously specify all the 4 values. In fact, I can only specify 2 out of the 4 values. Okay, simultaneously, each of which can be +1 or -1. Okay, so that means that the ground states now can be labeled further, and all of them commutes with the Hamiltonian. Okay, so the ground state is not only labeled by energy but by this x 2 out of the 4 operators, and therefore 4 degenerate. Okay, and they degenerate because of an operator which is this extended loop, and this degeneracy has nothing to do with symmetry, okay, of the kind that we are used to. Okay, and this is that 4-fold topological degeneracy of a Z2 liquid on a spin liquid on a torus, and it comes from the degeneracy of these 2 out of these 4 operators. Okay, and then if you take the degeneracy, basically this, if you take the degeneracy by some perturbation like this magnetic field, the gap between the different topological sectors is exponentially suppressed. Okay? And we can go into these details, but this is essentially the point that the topological degeneracy is robust. Okay. So that brings me to the end of the presentation. I'll go back to the board, and but before that, any question from this?
You can ask your question.
Am I audible, sir?
Yes, you are.
Sir, when you move the magnetic charge around the electric charge, does the direction matters whether you are going clockwise or anti-clockwise around it?
No, no. So basically, that it doesn't matter because the sigma x operators, you can write them in this direction, and if you reverse them, reverse their ordering, since they commute with each other, the direction doesn't matter.
Okay, thank you, sir.
More questions? Okay, so
Can I ask a naive question?
Yeah, sure.
Yeah. So what is the structure of the model that allows you to get this electric and magnetic charges of field, what you like to call? Is this the way I'm doing my mean field theory that essentially?
so then this is no mean field,
No mean
this is
field.
exact.
Right. So what is the structure of?
So the structure is hidden in the first statement that I made. is that the nature of the ground state. Okay. The nature of the ground state is this hugely superposed unwieldy state, which is very different from the symmetric state.
But this is unique, right? That's what you're
This
also
is
pointing,
unique.
right? So for the quantum case, it's unique.
Unique.
Okay.
So just like for the quantum magnet, it's unique up to symmetric breakings. Okay, this is unique. Okay, so there is no entropy, there is no symmetric breaking. Okay, and it has this weird properties.
So once we have such a ground state, which essentially implies that I can have this electric and magnetic charges, or what we call so-called theories.
It's the same thing.
So that's what I'm trying to say. So this kind of superposed unique ground states, right, essentially signals, right, that there would be such electric and magnetic charges.
Absolutely. Okay. It looks like that. So this ground state actually, just I'll point out one more feature of this ground state, and you would see that what is the real reason why this weird low energy theory, the case theory is emerged. Okay, and just point out it's basically a Gauss's law that emerges similar to. So more questions?
Can I just make a comment?
Yeah, sure.
So Subhro, when you were talking about this topological degeneracy, maybe it's good to point out that, of course, on a torus you have fourfold degeneracy, but if you just take it on an open plane, then
Unique.
it's unique,
Yeah.
right? So that's all. But,
Yeah, as I said that, I think that the one point that I made was this. So these operators are not defined on an open Jubilee.
Yeah.
Okay. So the question of topological degeneracy doesn't arise. No questions? Okay, good. Then let's move on.
Just let me make sure that
Yeah. Okay. Just let me know when I start. No, that's right. That's right. Let's make sure that. Okay, good. So let me just try to address the point that that raised is, and which is actually the central point about this weirdness. Okay, so made this very vague comment that you have superposition of entanglement. I'd like to sort of build up on that idea a bit more before we go on to the meat theory, because that's the central ingredient that we need to put into the meat theory. Okay. So when I say entanglement, I now need to be a bit more quantitative. What do I mean by entanglement? Okay. So what I really mean is a very weak signature of entanglement, which is like bipartite entanglement in problem. Okay, and this is entanglement entropy, not thermal entropy. Okay, okay. So this is basically a an extension of the APR type of idea, where I have two spins in a superposed state, plus or minus doesn't matter. Okay, and I calculate the entanglement of this. So I integrate out one of the spins. I get the reduced density matrix, and I calculate the entanglement associated with the reduced density matrix. So I take trace over 2, the entanglement, the density matrix, which is basically this is psi. The density matrix is psi psi. Okay, so this gives me the reduced density matrix of the first spin, and then I take this minus trace rho 1 log over. Okay. For this state, this would be log. That's the EPR entanglement for a bit there. Okay. So I want to extend this idea to the system. So I'll draw half line. So when I say that I draw a line, basically what I mean is that I have to be careful here, and this is where all these ideas about tensor product Hilbert space are very important. All the quantum field theories require to work harder with continuum field theories to do these things more carefully. But so if I have spins like this, okay, I just define a line like this. That's this line. So I know which spins are to the left of this line and which spins are to the right of this line with exact accuracy. Okay. You know that drawing this line becomes very difficult if I wanted to do this with a continuum field theory. Okay, that's the problem that quantum field theorists have, but not us. This is again because we have tensor product Hilbert space.
So it's not really dependent just on the tensor product, it's dependent on the locality of the degrees of
both the fact that
I can think of theories which don't have a tensor product structure.
Yeah, if you try to think about the gauge theories, even on a lattice, you would suffer from the same problem. You would have to include the charge sectors to mend the.
Yeah, but you can calculate the time.
If you include the charge sectors, okay, you have to make that. So you have to change the theory somewhat. So that's these two A and A bar, which are like 1 and 2, and then you have a take which is like this equal superposition. So all spins up plus some spins down, then so equal superposition of all of the kind that I wrote down. You take this state, form a density matrix like this, okay? But now integrating out, instead of integrating out only one of the two spins, you integrate out all the spins that are on the right hand side. Okay? So the density matrix is now a matrix with all the degrees of freedom on this right hand side, on this left hand side. Okay? And then take this, calculate this by entanglement. Okay? So let's first ask, what would I get if I calculated this entanglement entropy for our cartoon state? Up, down, up, down. So entanglement entropy for the state between A and A bar for the antiferromagnetic state like this. We see everyone agrees like this is a product state. Okay, so might look very intimidating that I have to integrate out those many spins and things like that. But since it's a product state, I can it just left side doesn't affect the right side. Okay, so this is exactly true for this. If this is not the exact ground state, I have some corrections. Okay, I get corrections which basically the corrections that get affected are like these bell pairs across the boundaries. Okay, across the boundaries, and instead of getting 0, I get some number which scales as the boundary of the partition. This is the famous area law of entanglement entropy. But this happens for symmetry broken states. Okay? So if we take the cartoon state, I get 0. If I get this, if I take the actual state, I'll get something proportional to the perimeter or the length of the bipartition. Okay? I get nothing else in the thermodynamic limit. Everything is sublime. Everything else is sublime. Okay? And notice that this entanglement entropy is a positive definite quantity. So whatever is sitting here okay, is a positive number, and one can think about changing the coupling constants to make this positive number very small. And one can conceive of taking the actual entanglement entropy, the area law, to 0 continuously. Okay. So it is because of this, the classical pictures that I draw to describe antiferromagnet holds and conveys information. And this is the reason why Landau-Ginzburg theory and mean field theory, the renormalization group calculations for the magnetic transitions that we know of works, because of this feature that they are not entangled for the thermal phase transitions. Okay. So a lot of the fantastic physics that we know about regarding phase transition work because of this. Okay, but let's. Sorry.
Can you call it bipartite by just splitting it into two
Yeah.
parts? Isn't it required that there should be two kinds of lattices on top of each?
No,
Or
just take this lattice and just do this partition. Okay, it's an extension of this idea. I have two spins. Okay, I make this partition between one and okay. You can make different kinds of partitions, etc., etc. But this is not. This is the simplest way. Okay, so that was about this state. What about this state? If I perform the same thing, okay, what about this state? So normally it would look like, again, this is the feature that the state at the superposition, but I'm only counting bell pairs across the boundary, so I would get an area law term. Okay, so if I now do the entanglement entropy A bar for this loop state, okay, entanglement entropy, I'll get something proportional to the length. But now you see that this state has one, this is not a completely arbitrary state. The state has one important information inbuilt into the wave function, which is as follows. These loops are closed, the loops of the downspins are closed, which means that if I draw the bipartition, the loops can either completely lie in A or completely lie in A bar, the complement of A, or they can cross. Okay, these are the three exhaustive kinds. But since the loop is closed, the number of crossing is an even number. Okay, and that cannot be changed. You can calculate the length of the loop, etc., etc. Okay, irrespective of the length of the loop, if you count the number of crossing, the number of crossing can be 2, 4, 500, but it cannot be 501. Okay. So the fact that this one qubit of information is inbuilt into this wave function, otherwise very arbitrary wave function, and that qubit of information does not add to the entropy. In fact, that's a negative contribution if one calculates. And you take this wave function, put it on a computer, you calculate this, you would find it's minus log 2. It's very important that it's minus log 2, which basically means that by changing alpha, okay, you cannot change it to 0, because at some point, if you try to change alpha too much, this would become negative. And we know that this cannot happen, which basically means that you cannot change this. Sorry, was the ferromagnet. This is for the loop state, which basically means that you really cannot change alpha to go from this state to a 0. Okay, in other words, you cannot deform this state to a product state. Whereas this state, this plus whatever, okay, the small corrections, you can deform this to a product state. Okay, this is the reason that all the things that we learned in Marvin-Ashcroft or things do not per se work for these things. Okay, this state that I said. So the low energy features are also very different, and that needs to be put into the mean. Okay.
Also, this argument doesn't require any symmetry.
this argument never requires any symmetry. Okay? Yeah. Yes. So you can break all kinds of symmetries in a Hamiltonian, and all these would work. Okay. So this is the central feature, that you're dealing with a state which does not have this cartoon product limit. Okay. So all our intuitions about single particles needs to be revisited. This is why I started from listing out the ingredients that we use in n-body physics. Okay. So if we are going to build the theory, and remember all the things that Arno pointed out, we can do the same argument for the ground state that he mentioned. Okay, it's a bit more complicated because it's a U1 state. There, but it's essentially the ideas are similar. Okay, that instead of this product state and the mean field theory, this product state, because it's a product state, you can have average expectation values at every point. That's what the order parameter is. Here you cannot. So you just cannot use order parameters. So if you are going to make a theory out of this, you mean field theory out of this, which is the starting point of your low energy field theory, then you have to take this entanglement into account and its manifestations, rather than the broken symmetry and the symmetry. Okay. Questions? So in the last 20 or 25 minutes, what I'll do is I'll point out how do you go about this mean field theory and connect it up to where Arun left with the slave rotor field theory. Okay. Questions? So I'll draw this is the EV scale at the Hubbard scale, and this is like 100 Kelvin, where it is a spin Hamiltonian, and then we are thinking about say 1 Kelvin, where in Arnold's case there were photons, magnetic monopoles, electric charges, etc. Magnetic monopoles, electric charges, etc. in Arnold's case. In this case, there are no photons, but there are Ising magnetic charges and electric charges. Okay. So this is the theory that we need to try and arrive at, starting from the spin Hamiltonian. And in this case, I have done exactly how to write terminal operators. Arnold has done somewhat approximately. I will try to point out the general structure. Okay. So whatever general structure that I would be valid must take into account the following features: the non-trivial entanglement of the ground state, fractionalization of excitations, which basically means that you have a single spin and you create more than one excitation. It's very different from the magnon. Okay. Emergent fermions, bosons, and whatnot. Okay. So we saw a fermion emerge at low energy. Okay. Possibly topological degeneracy. these are the features that any low energy theory, starting with the main theory, needs to account. And each of them are very different from. And I keep on saying, harping on the same point, that very different from this Cody-Weiss theory of the time. Okay. Okay. So the first question is that how do we do mean field theory without breaking symmetries? Okay. So that we can possibly address this. Okay. Let's try to see again in context of that exactly solvent model how this works out and then go forward. Questions? But I try to answer the questions. Okay, so we had this sigma, the product of sigma x operators and the product of sigma z operators. So z, 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 and x, 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 x. Okay. Okay. So let me write down the form of the low energy theory. Okay. See that at low energy, this description in terms of spins is meaningless because when it creates spins, it just creates many charges, 2 charges at a time at least. Okay. And so the description in terms of spins is not very useful. Okay. Instead, the description is the elementary objects are these electric and magnetic charges. So I would have to trade the spins for a description in terms of this electric and magnetic charges. Okay. So let's ask how to do that. Okay. So let's define. So on the sides of the square, I define operator, Ising operator mu x, okay, and on the bonds of the square, I mu x or mu alpha, okay, Ising operator on the sides. And on the bonds, I define an operator rho alpha. So this is on the sides and this is on the bonds. Two Ising operators. Okay. But now you see that this has a Hilbert space of 2. This has a Hilbert space of 2. Okay. So how many? So suppose there are n sides. So the Hilbert space of mu operators is 2 to the power n. Okay, if there are n sides. If there are n sides, then how many bonds do I have? 2n bonds. Like every side is associated with 2 bonds. Okay. So there are 2 to the power 2n rho operators. Okay. The Hilbert space of these rho and mu are this. The original Hilbert space, I had one Ising variable at every side. So the original Hilbert space dimension was 2 to the power 2n. So clearly, if I try to describe them in terms of mu and rho, which I haven't told you what they're good for, it just cannot be the right description because there are too many of them for my to faithfully describe my problem. So all of them cannot be independent. Okay, and this is the starting point of the Gauss's law, which is generic. So let me point out. So this is the problem. If I try to use them, then the description seems to be in terms of 2 to the power 3n. But my physical degrees of freedom are in terms of 2 to the power 2n. I still haven't told you beyond this vague idea that I want to use a description in terms of the electric and magnetic charges. Okay, I have said you that why I would like to do this. But the idea is that I want to explicitly describe in terms of electric and magnetic charge. Okay, so let me tell you one prescription to do it. You can find different other prescriptions, but sort of similar to this. Okay, so what I want to do is to write down my spin operators in terms of these new operators. Okay, and for this exact model, I can carry this out explicitly and exactly, which I'll then approximate first to the theory that Ono pointed out, and then the theory. Okay, so the three things. So I'll do this for the toric code. Then I'll do it for the U1 USL that Ono talked about. And then the generic structure, which is what the part of the structure. That's like the next 15 minutes. Okay. So this is, so I have sigma x, sigma z. So sigma z is easy to write down, mu x. So notice that if I denote the sites by I and j, the sigmas sit on the bonds. Okay, I, rho z, I, j, x. Okay, and in S is equal to okay, let's write down product of j belong to I, rho x I j is equal to S is equal to say, and so basically the spin operator. So this was product over j belong to R sigma x I j. So at every site I think about all the four bonds. I take the product. That was my AS operator. Okay. I now identify with this mu I operator, mu I z, which is a Ising operator sitting at the site. This is the easiest thing to identify. It's basically mu z is equal to +1 means AS equal to +1, which is like no electric charge. And mu z equal to -1 is like AS equal to -1, which is 1 electric charge. So this mu z counts the number of electric charge sitting at the site. So the mu z is the electric charge density operator, the Ising version of it. But it counts the electric charge density. So this counts the electric charge density. Okay. What about, in the electric charge language, sigma z created two electric charges. Okay. So it creates an electric charge. So if I act with the sigma z operator on this bond, okay, it creates electric charges here and here. Okay, that's the two ends. Okay, so and electric charge creation operator does not commute with charge density, it changes charge density. X, Z. Okay, so what about this rho? The rho says that you can create charges with different phases. Okay, you can act with the create the electric charge with minus phase, plus phase. It doesn't matter as long as you create two of them. Okay, and this becomes more physical when you think about the BP operator. It is the space for now. If I think about the BP operator, let's see, I, J, K, L. So it's sigma Z I J, sigma Z K L, sigma Z L, sigma Z J K L, sigma Z L I. If I use this, you see that mu I occurs twice. I is here and I is here. So mu I squares to 1. So if I try to write this, I get rho Z I J, rho Z J K, rho Z K L, rho Z L I. Okay. So the mu x's go away. Okay. But this, if you remember electromagnetism, this is like moving of a charge in a magnetic field, and this is the magnetic flux. Okay. The analogy becomes clear if I write rho as e to the power IA. This is what we are more familiar with. Here I can write it in this form, but A is not a continuous number, but either a 0 or a pi. Okay, if it's 0, then rho is 1. If it is pi, it's rho is minus 1. Okay? We can use all these tricks, but essentially the BP term is like the magnetic flux. Okay, and this rho is the vector potential. Okay, so this electromagnetism, this is an Ising version, much simpler than the Yuan version that we are used to from Jackson. Okay, is basically naturally takes the form of a case theory. Now I need to answer the question that this was 3n to the power 3n, the physical degrees of freedom were 2 to the power 2n. Okay, how do I account for that? Okay, so it turns out that all these degrees of freedom are not independent, because we know that if there is an electric charge, there is an electric field, and this is what Gauss's law tells us. Okay, so the Gauss's law for this mapping is basically product of rho x I j, j belonging to I at every site, is equal to mu z. So the charge at every site, so this rho z is like the is the vector potential, rho x is like the electric field, again conjugate to each other similarly. Okay, so this is the generic form of you can derive all the results that I did for this exactive solvent model using this mapping, which I have sort of presented ad hoc to you. But the advantage of this is that the magnetic degrees of freedom and the electric degrees of freedom, this is the magnetic flux and this is the electric charge, okay, they become more evident and easier to handle if you know, if you are familiar with case theories. Okay, it is explicitly written in terms of electromagnetic fields and charges, for which we know well-developed quantum field theory technology to handle in some more cases. In some cases, okay, beyond this integral form. But the point that I want to make is that this weird low energy excitations which had this Aharonov-Bohm phases, etc., are captured by a representation which is very different from spin waves, and in particular, all of them are endowed with a constraint like this, because it's a redundant description with the Gaussian law like this. This is the generic structure of the theory. Okay, and it is because of this constraint, okay, and the gauge charge structure, the generic form of the low energy theory is a lattice gauge theory, and in almost all the cases, actually all the cases that describes quantum field. Okay.
Is it useful to point out as well that in this language, if the charges can be separated out, then you have these weird phases, whereas if they cannot be separated out so easily, you can have conventional phases.
Yeah, sure. So here the point is that these three steps, okay, I have not done any approximation. Okay, this you can go. Everything again is polymatrices, so you can check that these are like very good. Okay, you can do this for arbitrary Hamiltonian, even for the Ising ferromagnet Hamiltonian that we are familiar with. Okay, it would just look horrible and completely unsolvable. Okay, and actually it would be impossible to solve exactly if you use this representation. Okay, just like if you use this order parameter description to describe a spin liquid, you would basically have to keep all orders of fluctuation. Can of course describe, but you won't be able to do a midfield theory. Okay, you have to keep all orders of fluctuations exactly to keep the entanglement pattern. Okay, it's not like feasible. Similarly, if you try to describe the symmetric broken phases in terms of these gauge charges, etc., you have to do more work. Okay, so it's not the right degree of freedom, even though it's a faithful representation of the spins. They're not the right way to think for the garden variety ferromagnets, etc. Okay, this is the point. More questions? Exhausted on the time, but can I take like
Yes, I so we have 3 more minutes official time.
okay, so
But you can take another 10 minutes. Right?
okay, fantastic.
Let us wind up by 15:30.
Okay,
Take a break for 15 minutes.
yeah, sure. Okay, so let's try to ask what is the similar. So the model that I use. I'll write it down. SZI, SZIJ, JZZ. This is on the pyrochlore lattice. Minus J plus minus, SI plus, SJ minus, SI. So if I take this, if I try to do the same decoupling in terms of mu's and sigmas, mu's and rhos, would I succeed? Okay. Answer seems to be that it's not correct to do that decomposition. Let's try to understand why. Okay. The decomposition that I did, particularly for sigma z ij, was mu xi rho z ij mu x. So these are Ising fields. All of these are numbers which are here. Okay. So suppose you did this decomposition and I did this decomposition of the same row, which is mu xi tilde rho tilde z ij and mu tilde k x, where the relation between your mu's and rows and the ones that I've introduced is as follows. Mu xi is equal to epsilon I mu tilde I and rho z I equal to epsilon I epsilon j mu rho z, where epsilon I is plus minus 1, and I can choose it as an how I like at every site. Okay, whatever choice of epsilons you give for different sites, plus 1 minus 1 plus 1 minus 1, whatever, it doesn't have to have a pattern. Okay, if I, with that choice, if I redefine the mu's and the rho's in the following way, okay, this and this gives the same value of sigmas. Okay, because I put this mu epsilon square 2 plus 1. Plus 1. So this means that this is another statement that these are redundant descriptions, but let me try to write this in a particular way. So, as I said, that any Ising variable can be written as e to the power I theta, where theta is equal to 0 or 1. Okay. Similarly, rho can be written as e to the power I a, where a is 0 or 5. Okay. So this epsilon can finally be written as epsilon e to the power I chi, where chi is 0 or 5. Okay. So this was on site, this was on bond, this is on site. Okay. So let's ask in this language, what is this transformation? Okay. So this transformation is like e to the power I theta going to e to the power I theta plus tau. Okay. This is e to the power I a plus chi I j chi I minus chi j. This minus sign is like a convention because e to the power I pi and e to the power minus I pi s a. Okay, but you see that this is how, this is exactly the kind of thing that Ono was writing down, except for this extra constraint. For him, everything was any number between 0 and 2 pi. Okay. Here, because we have this added constraint that all the Hamiltonian that I wrote down was explicitly involved only real operators, sigma z and sigma x. Okay, that's one place where to trace this for. So this is the reason why I got an Ising charge. Okay, and in fact, this relation is what is called an Ising gauge theory relation. Okay. Let's not go into technicalities, but this would not work for this thing where I have SY operators, which is all which has a complex representation, and I would need to do something else. Okay. So let's devise. So this was the, and I wanted to capture the electric, the magnetic monopoles, the electric charges, the magnetic monopoles, and the photons. Okay, so let's see how to go about this. So this is the prescription. Okay, as said, it's equal to E up to factor. The S plus, and I'll write it. So again, is like E pi I dagger e to the power I C E pi. Where let me actually write this. So let me use the same nomenclature as all of this. So I have the two tetrahedrons that she was drawing, and if I join the center of the tetrahedron, which are my sides I and J, okay, those are the spins are sitting on the bonds of this line. Okay, so that's the nomenclature I is J, and the S plus is like this. So this is almost what he introduced, but the full representation requires this, which he was not interested in, but I'll try to point out what these things are. Okay, so you see that he had this constraint that divergence, which is implemented by this first thing, divergence of E is equal to 0, coming from the fact that the Z for a tetrahedron was equal to 0. That's okay. If I take a tetrahedron like this, where I have 2 pointing out and 2 pointing in, okay, which is a SZ equal to 0 configuration. If I act with the S plus operator, okay, on this side, I flip this, and the total electric charge or the magnetic charge, whatever you call it, this electric and magnetic are interchangeable once you are consistent. Okay? So this divergence of E is no longer equal to 0, and this is what the electric the S plus and S minus operators do. So they create these electric charges. Okay, so and these are the electric charge creation operators. Okay, they change the electric charge density. Okay, so the electric charge density per tetrahedron is given by summation of J belonging to tetrahedron I, which is equal to the electric charge density, or we call it Q. Okay, so they change the electric charge density. Okay, and these in principle, in practice, if I flip this, then also the electric charge density is created in the neighboring tetrahedron. So I create electric charge density here and here, very similar to the AS operators. I flip a spin, I create 2 charges on the 2 tetrahedrons. Okay, but now these are complex bosonic charges. I can redo all the analysis that I did. I take 2 charges, move them around. I would see that they are bosons. I take an electric charge and a magnetic charge. I try to move one around the other. I'll see that it's a source of flux. All those things I can do, but it's harder to draw bioflow lattices, and that's an assignment. Yeah. So, but this is. But the crux of the matter is again this identification. That S plus is equal to this. There is this. There is this. Then there is this Gaussian law. You see that this is the generic structure of the identification, and the redundancy is now whatever all wrote down. Okay, it's essentially a U1 version of the same identification, the same representation that I used for the Tony code model. And in fact, I just mentioned that the thing that Arun pointed out, writing down the electric charge in terms of a rotor and the spin-on, okay, is, if I wanted to write this down in detail, I will write it as this. E to the power I. So this is a generalization of this idea. Okay, starting the simplest was this Todi code. This is slightly more complicated, but these are monopole operators on different sites. Here, it's even more generalized, where an electron operator, which is like a spin operator, okay, but it divides into two parts which carry different quantum numbers. This carries the charge of the electron, and this carries the spin of the electron. But it is again the same idea. Here, I divided the spin into two monopoles. For the Todi code model, I divided the spins into two electric charges. Here, I divide it into the charge of the electron and the spin of the electron. So you are you can entertain yourself by thinking about all the kinds of divisions that you can think about spins and electrons, and try to find out Hamiltonians which allow such fractionalization. And this, in fact, is one of the ways people have learned a lot about this field, by trying to find out different kinds of fractionalization. If it was a quantum Hall state, fraction of quantum Hall state, he would divide the same electron into three E over 3 particles for the 1/3 Laughing state. Okay, but again, the idea is same. You just choose whatever you want to do depending upon the energy and what the Hamiltonian wants. Very similar to the mean field theory, where you choose what kind of symmetry breaking you want to study. Okay, just that it's more weird because this is new, but the idea is same. You just enforce on the theory what you want to do. Okay, and the rest is pretty similar. You just incorporate this into these. So you just put this back into the Hamiltonian, and for this you would generate an interacting term. Okay, you just write everything there. So this I'm not writing, okay? But if I write down the j plus minus term, okay, I'll get phi I e to the power I j I j. So since so if I think about this, there is a suppose as on what's line, this is I and this is J. Okay, so the SI creates a monopole here, and an anti-monopole here. Okay? That's phi J. So this is I J. This is I, this is J. Okay, it creates this. Now, then there is another, this is minus is acting here, okay? So this is some KL, okay, nearest neighbor, okay? So, JL, it annihilates the monopole here and creates it here. The end result is like having a monopole here and here, okay? So, and this string operator. E to the power I K L into phi. So this is the form of the j plus minus operator. This is just E squared. This we don't know how to solve. This is the lattice case theory. So this is the gauge part, this is the matter part. This we don't know how to solve. Now we use the same techniques as mean field theory. Okay, we write. So this part, once we arrive at this part, now we can fall back to whatever we learned in mean field theory, what to sort of throw away, the fluctuations. Okay. we write this term as phi I dagger average value of I of A ij plus aj phi j plus average value of phi. These are my mean field instead of my symmetry or local order parameters. Okay, these are not order parameters at all. Okay. Now this is a quadratic problem. This part is actually something that we are taught in the 1 minute club. This is like once you take this as an effective hopping parameter. This is just the hopping model of the monopoles on the pi-flow lattice, some band structure. Okay. So this is going to give the band structure of the monopoles or the electric charges, what it is. This is what Arnaud was concerned with, and thinking about these fluctuations, which would give performance, because you would try to understand what is the fluctuations or what are the gauge fields doing, and you would get the ring excited term out of this. Okay. And this term renormalizes this contributes to the 0.61 whatever it calculates for the speed of light. This 0.61 etc. is all these numbers determine this renormalization. Is determined by this renormalization. Okay. But you have thrown away all fluctuations, which are now e to the power I delta of e to the power I a into delta of phi. Okay, those fluctuations we have thrown away. I mean, nothing new to this part. This is exactly what you threw away in the Fourier-Weisman field theory. Okay, you saw this. That's the mean field theory for the spin liquid, which does not break any symmetry, and it accounts for the fractionalization and all the things that we had listed. And this is where I stop.
Thank you. It's time for some quick questions, if any, or we can always disperse for coffee and ask questions there too.
But if there are questions from online people,
yes, we'll try to take that. Is there any questions from online? Any questions from online participants? If yes, you can just unmute yourself and ask. Seems no. Well, so then we break for a short coffee break and assemble here at 3:45.
yes. Thanks. Sorry.
No, that's fine.